In section 2.4, we begin to discuss the point-slope form of the equation of a line. We're introducing one new form. So far, we've talked about the standard form and the slope-intercept form. Standard form is a form that is often used in actually solving equations, and we will come back to the standard form in a later chapter when we solve systems of equations. So the standard form shows up mainly in those circumstances, but sometimes that's just the general form that an equation for a line is given in. The slope-intercept form, the nice thing about it was that from the equation we were able to determine the slope and the y-intercept of an equation of a line, or of the line, immediately. Okay? Now that allows us to go from an equation to a graph very quickly. But if we wanted to go the other direction, what if we had information about the graph or points that the line went through? How do we find the equation of the line? And the easiest way to do that is to talk about what's called the point-slope form of the equation of a line. So in this section, we're going to be able to create our own linear equations. We're going to be given information about the line, whether it's points they pass through, whether it's slope, maybe the slope of a parallel line, but we're given enough information to know what line we're talking about. But then we can use that to actually come up with the equation for that line. Once we have an equation, then we can answer a whole lot more questions about the model that we're setting up. Okay? So that's what section 2.4 is all about. The essential concepts for this lecture are the following. Use the point-slope formula to write equations of a line. Model the data with linear functions and use our functions to make predictions, and then to find slopes and equations of parallel and perpendicular lines. Alright, let's start by talking about the point-slope equation of some non-vertical line, meaning the slope has to be some numerical value, it needs to be defined, with a slope m and passes through a given point, a known point, x1, y1. That form for the equation is as follows. It's y, the variable, minus y1, which is the y-coordinate of your known point, equals m times the difference x, the variable, minus x1, the other known value from your point. Now the reason why this is called a point-slope form is that the information that you need to create this equation is a point m, a point x1, y1, and the known slope of m. If you know those two things, you can plug them into this formula, leave x and y as the variable, and you have an equation for the line satisfying that criteria. Okay, now why is that true? Imagine that you're given a slope of m and a point that you know your line passes through. Okay, so look at this on a rectangular coordinate system. Okay, so imagine there's some point out in space that you know, or in the plane here, that you want to be on the line, that you know is a point x1 and y1 that's on the line. And let's say just arbitrarily that my slope has basically this steepness right here. Let's say that's my line. Okay. Now recall that slope by definition means rise over run. So if I were to pick any other point on this line and calculate the slope between that point and the known point, I should get a value of m, right? So pick any point you want on here. And say I pick this one right here. And since I can pick any point at all, I'm going to let those be variables, right? X and y, because it's true no matter what point I pick on here. Okay? The slope between these 2 points should equal m. Right? That means m would be equal to y minus y1, that's the y-coordinate here minus the y-coordinate here, over x minus x1. Okay? Now if I multiply both sides of this equation that I have here, which I know is true by definition of slope, if I were to multiply both sides of this by x minus x1, and say this side by x minus x1, I would have the equation m times x minus x1 equals y minus y1, or if I just switch the order, right, I have y minus y1 is equal to m times x minus x1. That's where this equation right here comes from. All right? But the whole point here is, now if you're given the slope and you're given a point, you have the equation for a line by just plugging in to this equation. In this example, we are asked to write the point-slope form and then the slope-intercept form for the equation of the line with slope m equals 3 that passes through the point 2 comma negative 4. So to get the first answer, all we have to do is plug into y minus y1 is equal to m times x minus x1, an equation you are required to know whenever it comes time for your midterm exam. All right, so here's m. Now, this right here is going to be x1, y1, because that's the point. So y minus a minus 4 gives me y plus 4 equals negative 3 times x minus 2. All I did was plug in negative 4 for y1, negative 3 for m, and 2 for x1. So that's the answer, first answer to the question. That's the point-slope form of that equation. All right. Now, how do we get the slope-intercept form? Well, remember, and this is from your discussion board question this week, you got to know how to find the slope-intercept form, right? You've got to be able to find y is equal to mx plus b, because that's how you'd find the slope and the intercept for a given equation. Now, we already know the slope here, but we are still asked to find the slope-intercept form. Remember, all you got to do is solve for y. Okay, to solve for y, we will first simplify both sides, which means on the right-hand side, to take negative 3 times x, you get negative 3x. Negative 3 times minus 2 is plus 6. And then subtract the 4 from both sides to get y by itself. You'd have y is equal to negative 3x plus 2. All right, and clearly the slope is still negative 3. That doesn't change. And now you actually know the y-intercept from this equation as well. So that is the slope-intercept form. In this example, we have the same question again. We are asked to find the point-slope form and then the slope-intercept form of the equation of a line with slope m equals 2 that passes through the point 4 comma negative 3. So same process again. I'm just doing one more example. Start with the point-slope formula because that's the information that you're given. It's a point and the slope. Okay? So y minus, and here is your y1. Here is your x1, and of course there's your m. So y minus a minus 3 would be y plus 3 is equal to 2 times x minus 4. That answers the first question. That's point slope. Now to find the slope-intercept, solve for y. So I begin by multiplying out the right-hand side. It would be 2x minus 8. Subtract 3 from both sides, and y is equal to 2x minus 11. That is the slope-intercept form for that line. Write the point-slope form and then the slope-intercept form of the equation that passes through the points 2, negative 4, and negative 3, 6. Now, we've changed things up a little bit here because what you're not given here is the slope, right? You have been given 2 points. So how could we use the point-slope form in this case? Well, you have a formula for the slope, right? You have the formula m equals y2 minus y1 over x2 minus x1, right? Change in y over change in x. That gives me the slope, right? And once I have the slope, I still have at least one point. I can use the point-slope form. All right, so if you're given 2 points, start by finding the slope, right? So let's say this right here is x1, y1, and this is x2, y2. It doesn't matter which one is your first point and which one is your second point. Okay, it'll give you the same answer either way. But if I plug these in, I'm going to have 6 minus a minus 4 divided by negative 3 minus 2. Right? 6 minus a minus 4, negative 3 minus 2. That gives me 10, because 6 minus a minus 4 is 6 plus 4, divided by negative 5, which is negative 2. Okay? Now I have point and slope. The question is, which point do I use? And the answer is, it doesn't matter. Either point will work. Now, I've arbitrarily labeled this one to be x1, y1, so I'm going to plug it into my formula. Y minus y1 is equal to m times x minus x1. So that means y minus a minus 4, which would be plus 4, is equal to negative 2 x minus 2. That was my x1. So there's a point-slope form. Now, if you choose a different point, that is, if I chose this one, your point-slope formula may look different, but they're both correct, right? They would both be counted correct whenever you identify the point-slope formula. Now, the nice thing about the slope-intercept form is that it's going to be the same no matter which point you use. Because on the next step, if I wanted to find the slope-intercept form, everything will end up being the same after I simplify. That is, after I solve for y. So if I did y plus 4 is equal to negative 2x minus times minus is plus 4. All I did was multiply out the right-hand side here. Now I'm going to subtract 4 across from both sides, and I end up with y is equal to negative 2x. Okay? Now the point I was making before is that if you did this with the other point, instead of with x1 and y1, you stuck in x2 and y2 here, you'll get the same answer here. It may look different here, but they're both correct. So again, the point is you can use either point. Okay? Fantastic. Let's look at the next example. One more, same question, different information is given, but we have all the tools we need to answer this question. Let's write the point-slope formula and the slope-intercept form for the equation of the line that has the x-intercept 2 and the y-intercept of negative 1. That means if you were to look at this on a graph, you don't actually have to graph this to answer this question, but this tells me that my x-intercept is at 2, it's right here. My y-intercept is at negative 1, and I want to find an equation for that line right there. Okay, what equation represents that line? Well, even though it doesn't look like it, I mean, they're not ordered pairs here, they are still points, right? In fact, we can write them as ordered pairs. X-intercept of 2 has what coordinates? Well, it's on the x-axis at 2, and what's the y value of that point? It's 0. And the y-intercept is also a point, only it's 0, negative 1, because it's 0 left, right, but it's down 1. Now we have x1, y1, x2, y2, and the problem is just like the one above. We would start by finding the slope in our slope equation, rise over run, change in y over change in x. Change in y would be negative 1 minus 0. Change in x would be 0 minus 2. Make sure you do y2 minus y1, x2 minus x1. And I end up with negative 1 over negative 2, or 1/2. Now plug this with x1 into the slope-intercept form. Now why did I choose slope-intercept form? I could use the point-slope. In fact, I need to use the point-slope to get this answer right here. I could actually skip to the final answer pretty easily. But let's go ahead and go through the procedure by plugging in the point-slope formula. Because if I plug in the point-slope formula and I use y minus y1, I get y equals, or y minus 0 equals 1/2 times x minus 2. Right? There's the point-slope form. The slope-intercept form is simply multiply out the right-hand side, and since y minus 0 is just y, I'm actually going to be done after one step. x. 1/2 times a minus 2 is minus 1, and there's your slope-intercept. Now, what I was saying before was that I could have actually written this equation down immediately without going through this step, because I know the slope right here, and I know the y-intercept from the original statement of the problem, which I could have plugged in right here, right? Slope and y-intercept. But since it asked for both, I had to go ahead and do it fully in both cases. Okay, that's the point slope and the slope-intercept form of equation of that line right here. So let's review the different forms and types of equations of lines that we've seen. Okay, now the standard form was the equation form where you just had all the x's and y's on one side and all the numbers on the other. Okay, ax equal or plus by is equal to c. Y is equal to mx plus b is the slope-intercept form. Okay, a horizontal line has zero slope, so it generally looks like this, right? It's as if the m was 0. And a vertical line is one with no slope, and in fact it's different from this equation because you can't actually write down a slope-intercept form if your slope's undefined, but your vertical line is when x is just equal to a single number. And then your point and slope form is y minus y1 is equal to m times x minus x1. Now, different circumstances, you will use different forms of the equation. Okay, later on when we start solving linear systems, we're going to typically have things in standard form to begin with. When we want a unique form or a function form, slope-intercept tends to be the most commonly used. Obviously, if we're dealing with horizontal and vertical lines, those are the equations we'll look at. If we're trying to set up the equation of a line, this is the equation that we want to use, the formula we want to use. Okay, so we need them for different circumstances, and that's why we have different forms when they describe lines. Drugs are an increasingly common way to treat depressed and hyperactive kids. The lines graphed in this example represent models that show users per 1,000 U.S. children ages 9 through 17. Okay, notice that the x-axis, the horizontal axis, represents years starting in 1995. So a good natural choice for your variable would be years since 1995. So I would let this be 0, 1, 2, 3, 4, 5, and 6. That my x would represent that axis. The y-axis is the number of children out of every 1,000. So the starting point for stimulants like Ritalin means 24 out of 1,000 children were using it in our x0 point or in 1995. Okay, and we see a steady incline between these two. Actually, we're given the starting points and the ending points. We want to find the rate of change. That is, what's the number of children out of 1,000 per year increasing as we go from one year to the next. That's what the slope of the line is going to tell us. Okay, so slope of the line using stimulants. That's the blue line. Okay, that's going to be m is equal to y2 minus y1 over x2 minus x1. Now, what's the coordinate of x2, y2? Okay, I'm going to say this is x equals 6 and 34.2. This is x equals 0 and 24. Okay, so that's my x1, y1, x2, and y2 on part A. All right, which means 34.2 minus 24 divided by 6 minus 0. Notice the top number is the difference between year 2001 and 2005, and we're going to divide that by 6 because that's the number of years over which this occurred. So that's going to give me number of children out of 1,000 per year. All right, that's going to give me 10.2. 10.2 divided by 6 in my calculator gives me 1.7. Okay, so this means an average increase of 1.7 users per 1,000 children per year. Now let's find the slope of the line of children using antidepressants. Okay, same problem. M is equal to y2 minus y1 over x2 minus x1. Okay, so our points will be 0 and 8 and 6 and 16.4. So I take 16.4 minus 8 over 6 minus 0, or 8.4 divided by 6, which gives me 1.4. Okay, this is an increase of 1.4 users per 1,000 children each year, or per year. Either way you say that's fine. Notice they're not parallel. Even though you look at the picture here, they look fairly close, going in the same direction. You have Ritalin increasing higher than stimulants, or increasing at a faster rate than the antidepressants are. The stimulants are increasing in usage faster, which means the two lines aren't parallel. Now, when would lines be parallel? They would be parallel if the slope was exactly the same. So let's talk a little bit more about parallel lines and also perpendicular lines. Two distinct lines are said to be parallel if they have the same slope. Right? Obviously, if you have two lines, in fact, I'll just grab my line tool. This line and this line, well, maybe not quite. How about that line? Would be considered parallel if you graph them on a on a Cartesian system here. Say those were the two lines that I graphed. They're parallel because they have the same slope. Notice how they don't ever intersect means that they have the same slope, because the ratio of rise to run would be the same for these two lines, right? That means they have the same steepness. Okay? Two lines are said to be perpendicular if they intersect at a right angle. Now, what that means in terms of slope is that the product of their slopes is -1. So the slopes are what are called negative reciprocals. Now, I'll go into further detail in just a second, but let me draw a picture of perpendicular lines. Obviously, the first and fastest example of perpendicular lines is the axes for the coordinate system themselves, right? Because they form a right angle, right? But if I were to look at two lines out here in the plane, say here's my first line. Let me grab a straight one. There's my first line. I would say another line is perpendicular to it if the angle at which it meets is a perfect 1/4 of a full rotation, or what we call a right angle, right? These are perpendicular. Okay? And one way to write that is, if I were to call this L1 for line 1 and L2 for line 2, I would say L1 is perpendicular to L2. That's a mathematical notation for saying those two lines are parallel. Whereas over here, if this was L1 and this was L2, L1 would be parallel to L2. All right, now, what do I mean by negative reciprocals? Well, think about what two numbers multiply together to give me -1. If I had the number, say, 2/3, okay, what would I multiply by this to get to -1? Well, what you do is you flip the fraction. That is, you end up with 3/2, and you stick a negative out in front. Okay? In that case, you end up with what are called perpendicular slopes. Those would be two lines. This would have a slope of 2/3. This would have a slope of -3/2. So they're perpendicular to each other, right? That's what I mean right here. The slope of the perpendicular line, which I might abbreviate by writing M with my little perpendicular sign, would be -3/2. Now, what is the slope of the line that's perpendicular to a line with slope -4? What I do to figure that out is I write it over 1, and then I will flip the fraction 1/4 and change the sign. So negative becomes a positive. That's the slope of the line perpendicular to the line with that given slope. So a line with slope -4 is perpendicular to a line with slope 1/4. Okay? So it's just another way of describing what the slope of the line is going to be, is by telling you that you know it's either parallel to some known line or it's perpendicular to some known line. All right, so a type of question, I'll give you a couple here, where you're asked to find the slope of a line, or actually you're asked to find the equation of a line, but you got to know the slope to do it. One way they can tell you the slope is by telling you a line it's parallel to or a line it's perpendicular to. So let's do one of each of those kind. Write an equation of a line that passes through point 2, -4 and is parallel to the line whose equation is y is equal to -3x plus 5. Okay? Now anytime it says write an equation of a line, think point slope. Because that's how we find the slope, the equation of a line is by using a point and the slope. Now do we know both of those things? Do we know a point that the line goes through? Yes, check, we have it right here. Do we know the slope of a line? And the answer is not immediately, but yes, we can find it. Right? We can find it because we know it's parallel to this line. Now what's the slope of this line? Well, remember this. Y equals mx plus b. The number in front of the the number in front of the x is the m, it's the slope. So m is equal to -3, and we have the point 2, -4, so we have enough to plug into here. Right, we end up with y is equal to, or y plus 4 is equal to -3 times x minus 2. And if we simplify that, we end up with -3x plus 6. Subtract the 4 from both sides. We have y is equal to -3x plus 2. That's the equation of the line through this point. And if it doesn't tell you what form to put it in, I encourage you to always put it in slope-intercept form, because that's usually the best form for an equation to be written in. It contains the most information that you can get by just looking at it, which is a good thing. Notice how it's very similar to the equation we had here, right? It's y is equal to -3x, which makes sense because that's the slope part. But it's a different line because it has a different y-intercept. Now what if you were given the exact same problem, but we switched the word parallel with perpendicular? And we forget to put the t in there. All right. But mainly the concern, okay, we're changing parallel to perpendicular. All right, so what's the slope? Well, we know the slope from this line is -3. So what's the slope of the perpendicular line? Well, we go back up to negative reciprocals. What's the negative reciprocal of -1/3? It's of -3. If we write that as 3 over 1, it's going to be +1/3. Okay? So again, we have the slope and we have a point. We have enough to plug into the point slope formula. So we end up with y plus 4 is equal to 1/3 x minus 2. Okay, which I would accept, but if you want to simplify further, we can. Y plus 4 is equal to 1/3 x minus 2/3. 1/3 times the minus 2 is minus 2/3. Subtract 4 from both sides. I'm going to have to find the common denominator here of 3, so that's 12 over 3. I end up with y is equal to 1/3 x, and minus 2 minus 12 is minus 14 over 3. There is your equation of the perpendicular line through that point. So, again, by describing something as parallel or perpendicular, it's a new way of providing information about the slope. Okay? All right, that's the end of section 4 of chapter 2. In fact, that's the last section we're going to cover out of chapter 2, so that wraps up our working with functions and specifically working with linear functions.